Welcome to AI Frontiers, your trusted source for the latest and most impactful developments in artificial intelligence and machine learning research. In this episode, a detailed exploration will be undertaken of 17 influential papers, all published on May 15, 2025, under the Computer Science Machine Learning, or cs.LG category on the arXiv preprint server. These works collectively highlight the forefront of machine learning, spanning theoretical breakthroughs, advancements in efficiency, innovations in multimodal learning, new horizons in explainability, and a range of transformative applications. This episode is curated to engage practitioners, students, and scientifically curious minds alike, distilling complex topics into accessible insights. Over the course of this journey, listeners will be guided through the latest research themes, key findings, methodological innovations, and 3 particularly influential papers, all synthesized and analyzed by AI Frontiers expertise. Settle in as we begin a deep exploration of the frontiers of artificial intelligence, shaped by rigorous research and AI-driven synthesis. To set the foundation for this exploration, it is important to clarify what cs.LG represents and why it is central to contemporary AI progress. The cs.LG designation stands for Computer Science Machine Learning and serves as a dedicated category on the arXiv preprint server for research focused on algorithms and systems that learn from data, as opposed to relying on explicitly programmed instructions. This paradigm shift, enabling systems to infer patterns, rules, and strategies from examples, has become the driving force behind modern artificial intelligence. Machine learning powers a wide array of applications, including computer vision, natural language understanding, robotics, healthcare analytics, financial modeling, and climate science. The ability to train a system on thousands of examples, rather than manually coding rules for each scenario, has led to profound increases in adaptability and effectiveness. As a result, cs.LG research forms the heartbeat of AI's rapid progress, deepening our understanding of learning processes and expanding AI's societal influence. The first prominent research theme emerging from these papers centers on the theoretical foundations of machine learning, with a particular focus on formalizing learning processes as analogs to thermodynamic systems. Notably, Ziming Liu and collaborators have established links between the training of large models and the fundamental laws of thermodynamics, providing a mathematical framework that bridges physics and machine learning. In parallel, Yizhao Liu and colleagues have investigated the concept of superposition within neural networks, uncovering new insights into model behavior. These theoretical advances are not merely academic. They offer practical guidance for designing more efficient, reliable algorithms. Through the demystification of scaling laws and learning dynamics, this foundational work sets the stage for principled and robust approaches to the future of machine learning. A second major theme is the relentless pursuit of efficiency and adaptability within machine learning models. As models continue to grow in size and complexity, the associated computational, memory, and energy demands can become prohibitive. Researchers such as Mushang Chen and colleagues have introduced parallel scaling paradigms for language models, demonstrating that parallel computation can boost performance without proportionally increasing resource requirements. Additionally, Matteo Gambella and team have developed methods for incremental and adaptive learning, allowing models to update with new data while maintaining manageable sizes. These efficiency breakthroughs are enabling the deployment of advanced machine learning systems in resource-constrained settings, expanding the practical reach of artificial intelligence and ensuring that model scaling does not necessarily entail linear growth in computational costs. The third theme identified in this research collection is the rapid advancement of multimodal learning and synthetic data generation. In a world where data manifests as text, images, audio, graphs, and more, The challenge lies in developing models capable of reasoning across diverse modalities. Viba Bellavati and collaborators have engineered novel architectures for generating synthetic multimodal data, while Mugilan Ganesan and team have accelerated the alignment of vision language models through advanced self-distillation techniques. These efforts enhance the robustness of machine learning systems in low data and cross-modal scenarios, while synthetic data generation fuels improved generalization and innovation. As a result, models are increasingly able to handle the complex, heterogeneous data environments typical of real-world applications. A fourth central theme is the ongoing drive toward explainability and trustworthiness in machine learning systems, particularly as these models are adopted in high-stakes domains such as healthcare, finance, and autonomous vehicles. Songgun Kim and colleagues have presented PNPXAI, a universal explainability framework capable of automatically generating optimized explanations for a wide range of models and data types. User studies validate that these explanations enhance both trust and utility, marking a significant step toward democratizing interpretability across applications. As explainability becomes essential for regulatory compliance and ethical deployment, frameworks like PNPXAI are poised to make transparent, accountable AI accessible to a broad array of stakeholders. A fifth research theme encompasses both real-world applications and advancements in reinforcement learning. The breadth of machine learning's utility is demonstrated in works such as personalized health monitoring by Nazanin Zunamat Kermani and team, weather nowcasting using diffusion models by Randy J. Chase and colleagues, and multi-agent reinforcement learning strategies by Andrea Bicero and collaborators. These innovations are already impacting fields ranging from medicine and climate science to manufacturing and transportation. Reinforcement learning methodologies, in particular, are enabling more flexible and adaptive decision-making, allowing autonomous agents to excel in complex, dynamic environments. Collectively, these contributions underscore the practical and transformative potential of machine learning in addressing domain-specific challenges. Key findings from the analyzed papers reveal several breakthroughs poised to reshape the trajectory of machine learning research. The introduction of neural thermodynamic laws by Ziming Liu and colleagues unifies theory and practice in the training of large models, offering new ways to optimize learning dynamics. Parallel scaling laws for language models, as demonstrated by Musheng Chen and collaborators, pave the way for resource-efficient deployment of powerful models. Sangin Kim and team's PNPXAI framework marks a leap in universal explainability, while PharmaDith, introduced by Amira Alakdar and colleagues, accelerates drug discovery by generating molecules using pharmacophore constraints. Moreover, the work of Daniel Whitekamp and team on specialized learning mechanisms demonstrates significant improvements in data efficiency. Collectively, these findings address critical bottlenecks regarding efficiency, interpretability, domain-specific application, and theoretical understanding. Progress in machine learning has been propelled by a suite of advanced methodologies and tools, as evidenced by the papers under discussion. Diffusion models have emerged as versatile instruments not only for generating realistic images, but also for tasks such as molecule and policy generation, weather nowcasting, and drug design. Reinforcement learning continues to be central to training agents capable of handling complex decision-making tasks. Neural architecture search automates the design and adaptation of expandable networks, supporting ongoing model evolution as new data becomes available. Self-distillation techniques align smaller, more efficient models with their larger counterparts, improving speed and resource usage. Finally, explainability frameworks, exemplified by PNPXAI, leverage meta-learning and hyperparameter optimization to deliver robust, actionable explanations. Each methodology brings unique advantages and challenges, collectively pushing machine learning toward greater sophistication and practical impact. The first selected paper for in-depth discussion is Neural Thermodynamic Laws for Large Language Model Training by Ziming Liu and colleagues, published in 2025. This work stands out for its rare integration of theoretical innovation and practical utility. The study merges neural scaling laws with thermodynamic principles, introducing concepts like temperature and entropy to describe the training dynamics of large language models. These analogies are leveraged to explain and optimize learning rate schedules, providing actionable guidance for model training. By bridging physics and AI, the authors offer a robust, scientifically grounded framework that deepens understanding of how large models learn and generalize. The significance of this paper lies in its foundational impact, offering both explanatory depth and practical strategies to enhance the efficiency and robustness of large-scale machine learning systems. The second paper selected for detailed review is Pharmacophore Conditioned Diffusion Model for Ligand-Based De Novo Drug Design by Amira Alakdar and colleagues, published in 2025. This paper introduces PharmaDiff, an innovative diffusion model that generates drug-like molecules based on pharmacophore constraints without requiring detailed protein structures. By leveraging high-level pharmacophoric information, PharmaDiff outperforms traditional ligand-based design methods and accelerates drug discovery for novel or understudied biological targets. The use of transformer-based architectures enables the rapid exploration of chemical space, ensuring generated molecules align with desired pharmacophoric features. This work has been recognized for its novelty and real-world impact in the life sciences, exemplifying how machine learning is transforming the early stages of therapeutic development. The third paper highlighted in this episode is PNP-XAI, a universal XAI framework providing automatic explanations across diverse modalities and models, authored by Sang-Gun Kim and colleagues in 2025. PNP-XAI is designed as a plug-and-play, universal framework for explainable artificial intelligence. It automatically selects and optimizes explanation methods for any model or data type, supporting a wide array of attribution and interpretability techniques. Extensive user studies confirm that PNP-XAI increases usability and trust, making it deployable in critical sectors such as healthcare and finance. The broad applicability and societal relevance of PNP-XAI mark it as a foundational advancement in the pursuit of trustworthy and transparent machine learning systems. By automating the selection and optimization of explanations, this framework lowers barriers to adoption and fosters confidence in AI-driven decisions. Looking ahead, several future directions are anticipated to further shape the evolution of machine learning. Key opportunities include the integration of foundational theoretical insights with practical optimization techniques, which will inform the design of more principled and effective learning systems. Expanding explainability and trustworthiness in high-stakes domains remains a priority, as does the pursuit of adaptive, data-efficient, and human-like learning algorithms. Balancing scalability with accessibility and fairness is an ongoing challenge, particularly as machine learning becomes more embedded in diverse social and economic contexts. Interdisciplinary and responsible innovation, bridging computer science with fields such as physics, biology, and the social sciences, will be essential for ensuring that advances in artificial intelligence benefit all segments of society. The synthesis and review process for this research overview involve the combined strengths of advanced AI tools and human expertise. OpenAI GPT 4.1 was utilized for initial summarization and structural organization, with TTS synthesis and image generation supporting the podcast and accompanying visuals. Human experts conducted thorough reviews to ensure accuracy and clarity, though some minor oversights may persist. All referenced papers from the arXiv preprint server are cited appropriately. This AI-human partnership exemplifies a commitment to depth, transparency, and critical insight, ensuring that the content delivered is both reliable and accessible. thank you for joining us at AI Frontiers as we journeyed through the latest frontiers of machine learning research. To stay informed about the most current developments in AI and machine learning, subscribe to our channel for expert analysis and accessible insights. AI Frontiers is your destination for daily updates, providing critical perspectives on breakthroughs and trends in artificial intelligence. In this podcast, we bring you the latest breakthroughs in computer science and AI straight from arXiv. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses arXiv.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by arXiv.org.